This video is an opportunity to get some practice with electron configurations and orbitals. The video is set up for you to work one of the practice problems, answer an Edpuzzle question, and then the video will progress to allow you to see the answer to that particular question, check your work, and there are some explanations embedded as well. If you haven't already done so, open a window that has the practice questions. You can either print this or you can just answer the questions on a separate sheet of paper. So go ahead and work question number 1, which relates to a different representation for energy level diagrams. With this question, we take a look at some shorthand ways to represent the energy level diagram. So read the information here and answer the questions that are embedded. The first two questions that went with number 1 involved drawing a Bohr model for the atom that goes with each of the diagrams, one for silicon and one for copper. To try to make the answer key easier to read, I simply labeled how many electrons would be in each of the energy levels. So following the energy level diagram for silicon, the first energy level you should have drawn 2 electrons, the second one should have 8 electrons, and the third one should have 4 electrons. You may have drawn those as dots, and that's just fine. I thought it was a little easier to read if I put the numbers in. The Bohr model atom that goes with the box diagram shown for copper, you have 2 electrons in the first energy level, 8 in the second energy level. The third energy level has 17 electrons, which is 2 here, 6 here, and another 9 over here for a total of 17. And the fourth energy level has 2 electrons shown there with the 4s. C, D, and E kind of all go together. We need a box diagram for nitrogen. Big thing here is to make sure that when you distributed the electrons into the 2p sublevel, that you gave each orbital 1 of the 3 electrons. Phosphorus looks somewhat similar. It also has a configuration that ends p3, and then that sort of feeds into the next question, which is the similarities and differences. Both of the diagrams end in a p sublevel with 3 electrons. They both have 5 total valence electrons, and the difference is that nitrogen has 2 energy levels while phosphorus has 3. To connect that with our periodic table, we observed that both elements are in column 15, so they have 5 valence electrons. Nitrogen is row 2, so it has 2 energy levels, whereas phosphorus is row 3, so it has 3 energy levels. And lastly, here is a box diagram for iron. Notice again that when we get to the 3D sublevel, we gave every orbital 1 electron before we went back and put a second electron into one of those 3D orbitals. You want to keep this box diagram for iron handy as we move on to the next question. In this next question, I have attempted to draw a connection between the energy level diagram and the orbital shapes for iron. I've taken each of the s sublevels and tried to draw a picture over the top of those electrons that represents each of those s orbitals. The s orbitals are spherical, so I put in what looks to be a sphere, and as we move from the first energy level to the fourth energy level, you'll notice that the spheres look pretty much the same, but they're getting bigger and bigger and bigger. At the p sublevel, we have 3 orbitals oriented mutually perpendicular to one another on the x, y, and z axis. And so I've tried to represent those 3 orientations here, 1 orbital per line. As tempting as it is to think that the lobes are there to accommodate sort of 2 electrons because you have 2 lobes, it really doesn't work that way. The electrons are moving around constantly. There are times that both of them are in the same lobe. There's times that they're in opposite lobes. So as I drew these orbitals, I tried to represent all those possibilities for you. When we get all the way up here and we have the d orbitals are pretty fancy, so that was my attempt to draw them. And if you were to take all these orbitals and put them together and try to assemble sort of what an iron atom would look like, you'd have to take all this junk and stack it over the top of the nucleus in the center of this thing. And so with my limited artistic skills, this was my attempt to overall represent the iron atom. These are the line diagrams that I was using to draw my shapes of the atomic orbitals. Admittedly, mine don't look a whole lot like that, but that gives you some idea what I was trying to represent. I would like you to create a box diagram using this idea for nitrogen, much like I did above for iron. You can use these little line drawings to help you, and try to make sure that, like mine, yours incorporates the idea of the different sizes. Here's my drawing. I chose to draw it more like a box diagram than an energy level diagram. If you stacked it up, that was just fine. Obviously much simpler than iron because we don't have any of the d orbitals. And then for number 3, take these, stack them together, and assemble them with all the orbitals centered on the nucleus. This is my picture. It got a little messy. I tried to draw the electrons to match the same color as the orbital that they're sitting in. So in here is the 1s orbital. It has these 2 electrons. The 2s orbital looks just like the 1s. It's the purple one. And there's the 2 purple electrons. And then when we get to the 2p sublevel, there are 3 orbitals here. There is a blue one right there, a green one, and a red one. Each one of those has 1 electron in it. So those are represented by the red, the green, and the blue electron. Those 3 electrons are split between the 3 orbitals. For question number 4, I would like you to write the electron configuration, identify the valence shell, and the number of valence electrons in each of the following elements. Here are your answers. Take a minute, check your electron configurations, as well as your valence shell and your number of valence electrons. Remember that sometimes the number of valence electrons is not necessarily the last term in the electron configuration. For example, cobalt, your last term is a 3d7. However, the valence electrons are in the 4th energy level. And sometimes for things like phosphorus, you have to add up 2 pieces of the electron configuration, this 3s2, 3p3. They're both part of the 3rd energy level for a grand total of 5 valence electrons. Next, please write the shorthand electron configuration for vanadium. Vanadium is 1 row below argon in the periodic table, so argon is our reference point. We have argon 4s2, 3d3. Do the same thing for selenium. Selenium is also 1 row below argon in the periodic table, so argon is the reference point for that one as well. In this case, we have 4s2, 3d10, and 4p4 to get ourselves to 34 electrons. Take your electron configuration for selenium and change that to match selenide, the S2- ion. This one you simply have to add 2 more electrons to the electron configuration for selenium to represent the 2 electrons that are added when forming the selenide ion. And for number 8, name 1 element and 1 ion which are isoelectronic with selenide ion. The element here, you only have 1 choice. You need to find an element that has 36 electrons. Element number 36 is krypton. So the element that's isoelectronic with selenide is going to be krypton. The ions, you have a number of different choices. You're looking for ions that have 36 electrons. So look at the elements near krypton on the periodic table, and you'll find that if you take away or add the appropriate number of electrons, you end up with an ion that has 36 electrons.